Okay, sound waves travel with a constant velocity through air. The speed of sound depends on the temperature of the air, and the air itself is moving. The speed is added to the speed of sound, or subtracted from depending on the direction that sound travels relative to the air. Suppose that it is very cold weather, so that the speed of sound in still air is 300 meters per second. You stand in front of a tall vertical cliff that is 3,600 meters away. At t equals 0, you shout at the cliff, and at sometime later, t equals big T, you hear your echo. So first let's sketch this. What's this look like? Well, we have this person, and we have this big cliff, and then this whole distance here is going to be 3,600 meters. Okay. Well, we have distance. Let's see. Suppose the air is still. Calculate the time t and the average speed of the sound wave. Well, if we yell and our sound wave is going in this direction at 300 meters per second, how long is it going to take to hit the wall? We know d equals the distance over time. If we solve for time, then we get t equals d over v. So the distance, 3,600, divided by 300, the speed that it is moving on a very cold night, becomes 12 seconds, right? That's not the right answer, but that's the line of thinking. The right answer, if we yell at the wall and it takes 12 seconds to get there, remember, it's an echo, so we hear it sometime later. So now the sound has to be traveling in the opposite direction. Has the speed changed? No. It's still just 300 meters per second, but our distance has changed. So we can just double this. We can just say T1 is 12 seconds and big T is 24 seconds, because it's got to make the round trip. It's got to go there and it's got to come back. Now for B, suppose the air moves toward the cliff with a speed of 60 meters per second. So now we're dealing with wind. So now we have 300 meters per second, just the speed of sound. Sound is the vibration of air particles moving through the air. So we have 300 meters per second, and then we have 60 in the same direction. So what is the total velocity? To the right, it is going to be 360 meters per second. Okay. Calculate the total time and the average speed of the sound wave. All right, so for the first part, we are moving in this direction with 360 meters per second for 3,600 meters. So we have a velocity and we have the distance. Velocity equals distance over time, and we're going to use the same t equals d over v. Same equation here. So we get the time to get to the cliff is going to be 3,600 divided by 360, because we're moving in the same direction. There's our zero trick, 3,600, and that's going to give us 10. Don't forget to write your units. So 10 seconds. 10 seconds to get there. On the way back, now we're moving in the opposite direction, so our vectors are going to look a little bit different. So now, not the highlighter, now we have 60 meters per second in this direction. Well, that means we're moving at 240 meters per second for our velocity. So this becomes, the distance is still going to be the same. It's still got to travel 3,600 meters to come on back, but now it's going to be 240 meters per second, and that total time, 3,600 divided by 240 gives us 15. So T2 for the way back is 15 seconds. Does that make sense? Yeah, it does. It should be shorter to get to the cliff than it is to come back, because when the sound wave comes back, we're having to fight the wind. So we have 15 plus 10, and the total time is 25 seconds later. And probably by 25 seconds later, you're not able to hear the echo. You're not paying attention, or there's other noise, or you didn't yell loud enough so it loses some of the energy by the time it gets back. But there it is, 25 seconds. C, the average speed when there is wind should be less than the average speed when there is no wind. Why is this the case qualitatively? So that's what we just did. So hopefully you can just put that into words using greater than and less than. I think I just did that. So that's it. Keep it nice and short.